Okay, in this video, we're going to be talking about progressive waves, transverse waves, longitudinal waves, restoring force, and equilibrium. So, progressive waves, we're going to be talking about transverse waves, we're going to be talking about longitudinal, we're going to be talking about equilibrium position, and then we're going to be talking about restoring force. All right, so these are the 5 key words we're going to be talking about today. Okay, so what is a progressive wave? Okay, so a progressive wave is one that transfers energy and it would need a medium, and in some cases it could be just a vacuum, and the particles don't vibrate. Sorry, they do vibrate. So the particles they vibrate, but they don't move along the wave. Okay, so the progressive wave, it transfers energy, it needs a medium, and in some cases a vacuum. The particles vibrate and they don't move along the wave. So that's number 1, that's 2, and that's 3. What is a transverse wave? Right, so let me just demonstrate. So assuming that this is an equilibrium position, I'll tell you what equilibrium means in a moment. So assume that this is an equilibrium position and it's vibrating about the equilibrium position. Now, at the moment it's oscillating, but it's not really transferring energy yet. So if it's transferring energy left to right, it will be moving like this. So it's moving up and down, and it's moving left to right. So transverse wave, how do we say this? So transverse wave, okay, so transverse wave is where the particles or the wave is oscillating about the equilibrium position perpendicular to the energy transfer. Okay, so transverse wave is where the particle or wave is oscillating about the equilibrium position perpendicular to the energy transfer. What about longitudinal wave? So, all right, let's just draw the transverse wave first. The transverse wave, well, it's like this, isn't it? So the transverse wave is this. So it's moving up and down. So let's just say that's moving up, that's moving down. But the energy transfer is here. So this is energy transfer, and because it's moving up and down, that is the motion, and this is the transverse wave. Now for longitudinal wave, so rather than going this way, what it's doing is that it's moving this way. So it's moving parallel to the direction of transfer. So if I draw a longitudinal wave, So here you've got compression. Here you've got, so here, because it's bunched close together, is a compression. Here is the rarefaction. And the compression is where it's high pressure. So it's high pressure. And here it's low pressure. Okay, so rarefaction is low pressure and compression is high pressure. And for longitudinal, how would we say this? So for longitudinal, it's exactly the same thing as here, but what do we swap? So instead of perpendicular, we say parallel. Okay, so for transverse wave, you say the particle or wave oscillating about the equilibrium position perpendicular to the energy transfer. If it's longitudinal, is a particle wave oscillating about the equilibrium position to the energy transfer. So you swap parallel when it's longitudinal, and if it's transverse, you say perpendicular. So here it is moving this way, it's moving left to right, that's parallel. If it's transverse, it's up and down, but it's moving along this way. All right, we still need to do two more terms. What is equilibrium position and what is restoring force? Right, so if we draw a spring, and let's hang a mass from it. So what's the force acting down? It's not gravity, it is weight. So the weight is acting down, and in the spring there's tension, and that's acting up. Now, because it's hanging, it is in equilibrium. And what does that mean? That means the weight is equal to the tension. So the weight is equal to the tension. Okay, so the weight is the force acting down, and there's also another force acting up, and that's the tension in the spring. Because you've let it hanging, and assuming that it is not accelerating, it's not moving, there's no force, there's no resultant force. That means it's equal. So the weight is equal to tension. Now, if you've done Hooke's law and you've done F equals ma, you can say that the force from Hooke's law, you can say F is equal to kx. And then down, you can say that the weight is equal to mg. So what you could say is that mg is equal to kx. That is what you could say. All right, so what do we mean by equilibrium? Well, let's just explain a bit further. So here you've got the spring and you've got the mass. So you've got the weight, mg, so W equals mg. This is the equilibrium position. Now, supposing you pull the mass down. So this is the spring, and you've let the mass hanging down, right? So now, assuming that this is the mass, once you've let it go, what it does is that it moves up, goes down, it goes up past the equilibrium position, it goes back down, and so it will oscillate. So it will oscillate like this. So this is the equilibrium position. This is the equilibrium position. I've shortened it down. So that's equilibrium position. Now the spring will stretch, and let's just say, yeah, This is x. Okay, so the restoring force is this force pulling it back up. Because you've got the weight is still W equals mg. So you've pulled it down. Now, once you've let it go, it will go back up. It will go back up. Once it passes through the equilibrium position, it will start to slow down again, and there will be another force acting down this way. So you could say that equilibrium position is in between these 2 points. Okay, so what is the equilibrium position? You can say when it's at rest. So when it's at rest, or where all the forces are equal, where the sum, so you can say where the sum of the forces is equal and opposite. So it is at rest because the sum of the forces is equal to 0. What do we mean by restoring force? The restoring force is the force needed to bring back to equilibrium. So that is number 5.